In the early months of 1945, somewhere in the waters surrounding Japan's home islands, disaster struck an American fighter pilot. His F-4U Corsairs engine had given up mid-combat. The fighter plunged toward the cold Pacific below. He ejected just as the aircraft hit the surface, watching metal disappear beneath the waves. But the story didn't end there. Japanese patrol boats raced to the wreckage site within hours. What they pulled from the water would become one of the war's most critical intelligence prizes. For almost 3 years, Japanese pilots had tangled with this American fighter above the Solomon Islands, in the Philippines, and across the home islands. They'd grown to respect it, maybe even fear it. Its speed was impressive. Its guns packed tremendous firepower. Its airframe seemed nearly impossible to break. Yet they'd never had the chance to see one intact, to take it apart piece by piece, to really understand what they were up against. This wasn't just a story about salvaging an aircraft. It was something far more significant. It was Japan's aviation specialists coming face to face with a hard truth. That moment when technical professionals had to confront just how far the technological gap had actually grown. What Japanese engineers would learn through examining this fighter would shake their confidence. Manufacturing techniques they'd overlooked. Materials science they'd underestimated. Design philosophy they hadn't anticipated. This captured Corsair represented the peak of American fighter development. Born from a 1938 Navy specification, the aircraft had evolved from an experimental concept into one of the Pacific War's most formidable combat machines. That inverted gull wing caught the eye immediately. The massive Pratt & Whitney R2800 double wasp engine. Everything about it screamed advanced technology. Most striking was what Japanese specialists understood but couldn't quite replicate. The Corsair had found something their own aircraft couldn't quite balance. A genuine equilibrium between raw speed, hitting power, how far it could fly, and how strong its structure really was. It all started in 1938, when the Navy's Bureau of Aeronautics asked manufacturers a bold question. Could someone build a fighter that could fly faster than 400 miles per hour while still functioning from aircraft carriers? At that moment, most fighters struggled to even reach 350. The specification demanded more, though. Low landing speed for carrier work, 1,000-mile range, serious armament, the ability to haul bombs. Chance Vaught's answer was daring in its simplicity. They'd build the aircraft around the single most powerful engine they could find. That Pratt & Whitney R2800 double wasp produced 2,000 horsepower, nearly double what most contemporary fighters generated. Feeding that power meant a propeller unlike anything else, 13 feet and 4 inches in diameter, enormous. Bigger than any other fighter had ever used. That created an immediate problem. How could they keep the landing gear short enough for carrier operations while giving that massive propeller clearance from the deck? The solution became iconic. Rather than conventional straight wings, designer Rex Beisel's team inverted the whole concept. Wings angled downward from the fuselage, then leveled out. That M-shaped profile when viewed head-on. It allowed short gear, gave the propeller room, and created something aerodynamically elegant too. That transition where wing met fuselage generated minimal drag. The prototype, the XF-4U-1, first took to the air on May 29, 1940. Test pilot Lyman Alouette flew it out from the Stratford, Connecticut factory. During a later test flight in October between Stratford and Hartford, the aircraft hit 405 miles per hour. Headlines celebrated it as the first American single-engine fighter to break that barrier. The actual maximum speed in level flight was 378 miles per hour at altitude. Still remarkable for 1940. Combat-ready Corsairs started reaching Marine squadrons in late 1942. VMF 124 got the first operational examples and deployed to Henderson Field on Guadalcanal that February. The Corsairs' first real fight came quickly, and it was rough. February 14, 1943 became known as the St. Valentine's Day Massacre. 9 American fighters went down, 2 were Corsairs, P-38 Lightnings, P-40 Warhawks, and bombers fell too. The Japanese lost 1-0. That 9-to-1 ratio stung. Daylight bombing missions paused while tactics got reviewed. Superior machines alone didn't guarantee victory. Experience, tactical knowledge, and smart deployment mattered just as much. American pilots adapted. They figured out what the Corsair could really do. It wouldn't outturn a Zero in a slow-speed turning fight. That wasn't its strength. Instead, pilots learned boom and zoom. Climb high, build speed, dive on the enemy, fire, then use that speed advantage to escape before the Zero could respond. Second Lieutenant Kenneth A. Walsh of VMF 124 mastered these tactics. His first kill came May 13, 1943, and he'd eventually rack up 21 victories flying the Corsair. As 1943 and 1944 unfolded, the Corsair's legend grew. Marine squadrons spread across the Solomon Islands, operating from rough coral airstrips hacked from jungle. The Corsair's ruggedness proved devastating in their hands. It could absorb punishment that would splinter Japanese fighters. 650 caliber machine guns gave it tremendous firepower. 4 inboard guns held 400 rounds each. 2 outboard guns carried 375 rounds. That totaled 2,350 rounds of ammunition. Later models swapped some guns for 20mm cannons, though many pilots stuck with the 50 caliber weapons for their reliability and ammunition capacity. The Corsair did more than just fight for air superiority. By mid-1944, they regularly carried external stores, a 1,000-pound bomb on the centerline, rockets under the wings, napalm canisters, fighter-bomber capability that became invaluable during amphibious landings. When the Okinawa campaign kicked off in 1945, Corsairs flew thousands of ground attack missions. Grateful infantrymen called them the Angels of Okinawa. What Japanese pilots witnessed in combat told only part of the story. From a Zero's cockpit, they saw an opponent that outran them, outfought them, outlasted them. But grasping how and why required examining the aircraft itself. Japan's technical research centered on 2 facilities: the Yokosuka Naval Air Technical Arsenal south of Tokyo and the Army Aviation Technical Research Institute at Tachikawa. Throughout the war, they'd been pulling captured Allied aircraft from Pacific battlefields, learning what they could. Most captures were wrecks, bent and broken, salvaged from crash sites. An intact operational American fighter was unprecedented. The Yokosuka Arsenal had been Japan's premier naval aviation research center since 1932. By World War II, thousands of engineers and technicians worked there. They'd designed numerous Japanese naval aircraft, though actual production happened at companies like Mitsubishi and Nakajima. These were serious professionals who understood aircraft design at the highest levels. When a salvaged Corsair arrived at Yokosuka in early 1945, it represented something extraordinary. Here was one of the newest American fighters, relatively intact despite water damage from its forced landing. Recovery crews had kept it from sinking completely. Now it sat in Yokosuka's secure technical section, waiting for examination. The first work involved careful assessment. Saltwater immersion had damaged some systems, but the fundamental structure remained sound. The massive Pratt & Whitney engine would need complete disassembly and thorough cleaning. Most importantly, the airframe showed no combat damage. This mattered enormously. Previous captured American aircraft had often arrived torn apart, making it impossible to tell design features from battle damage. Japanese specialists began methodically. Every dimension got recorded. 40 feet, 11 3/4 inches of wingspan. 33 feet, 4 inches long. 15 feet tall with wings extended, 16 feet 2 1/4 inches when wings folded up for carrier storage. That inverted gull wing demanded immediate attention. Japanese designers grasped the aerodynamic benefits. They understood the structural advantages. But they also recognized something else. Manufacturing that shape demanded sophisticated tooling and quality control beyond what most Japanese factories could reliably handle in 1945. The examination turned up something that genuinely surprised the technical team. Despite being advanced, portions of the Corsair's outer wing surfaces weren't metal at all. After the main wing spar and ammunition storage areas, both upper and lower surfaces used fabric covering. So did the control surfaces, ailerons, elevators, rudders, all fabric. Japanese specialists initially found it puzzling. By 1944, modern fighters had moved to all-metal construction. Further analysis revealed sophisticated reasoning behind it. The fabric covering was deliberate. From the aircraft's 1938 to 1940 development period, it represented intelligent thinking. Weight savings where structural loads remained minimal. Engineers preserved aluminum for critical load-bearing components. The fabric itself was specially treated. When properly applied, it provided sufficient strength and weatherproofing, while weighing significantly less than metal skins. This showed mature judgment about resource allocation for maximum performance. When technicians disassembled the wing structure, they encountered construction methods that impressed and disturbed them in equal measure. The main wing spar carried all the flight loads. It was a massive aluminum alloy, forging of exceptional quality. American metallurgy had achieved something Japanese facilities couldn't easily match. The spar's dimensions and load capacity exceeded comparable components in Japanese fighters. That single piece told a fundamental story. American industry could produce large, complex forgings with consistent quality. Japanese manufacturers increasingly relied on built-up structures assembled from smaller pieces. The wing's internal framework showed similar sophistication. Aluminum sheet ribs had been stamped with remarkable precision. Each one was virtually identical to the next. Tight manufacturing processes, consistent quality control across the board. Japanese aircraft production had become increasingly unreliable as the war wore on, with each plane showing different levels of quality in its components. The focus shifted to examining the Corsairs' weapons system. 6 Browning machine guns, each firing .50 caliber rounds, were mounted across the wings, a devastating array of firepower. What made this installation remarkable wasn't just its raw power. The entire system had been engineered as a unified whole. Ammunition containers, feeding mechanisms, cartridge ejectors, and charging systems all functioned together without friction. Every part seemed designed to work in concert with the others. These guns represented American precision manufacturing at its finest. The Browning M2 had evolved over decades into a refined design, produced by the millions with extraordinary consistency that Japanese factories simply could not match. American ordnance makers had achieved reliability standards that Japanese technicians could only admire from a distance. Japanese engineers also noticed something else that caught their attention. Beneath the cockpit lay 150 pounds of armor plating. Behind the windscreen sat thick, bullet-resistant glass, nearly 1.5 inches deep. This spoke volumes about American design philosophy. Japanese fighters had largely discarded heavy armor in pursuit of lighter weight and superior agility. The Zero's early victories seemed to prove this approach correct. But as American fighters grew stronger and better armed, that lack of protection became a death sentence. The Corsair showed that exceptional engineering could blend substantial armor with impressive performance, possible only because of the massive power plant driving it. That engine deserved careful study. The Pratt & Whitney R2800 Double Wasp represented the pinnacle of American aero engine development. 18 cylinders split into 2 rows of 9, displacing 2,800 cubic inches and churning out over 2,000 horsepower. This was mechanical engineering elevated to art. Japanese technicians had seen this engine before in salvaged American aircraft, but never in condition good enough for thorough examination. What they discovered about its construction seemed almost beyond comprehension. Each cylinder had been machined with tolerances so tight they measured mere thousandths of an inch. Pistons, rods, and crankshaft components displayed surface finishes and dimensional precision that pushed beyond what Japanese engine makers could consistently produce. The twin-stage supercharger system maintained power at extreme altitudes through an elaborate network of internal passages and perfectly calibrated rotating parts. Japanese efforts to build comparable superchargers had largely collapsed under the weight of their own manufacturing limitations. What impressed most was simple reliability combined with raw power. American radial engines routinely delivered their rated horsepower for hundreds of hours before needing attention. Japanese engines, even fresh from assembly, frequently fell short of their theoretical output and demanded constant maintenance. The R2800's steady performance flowed from superior metal alloys, better oils, tighter manufacturing processes, and rigorous quality checks at every stage. Even the propeller system revealed advanced thinking. The Hamilton Standard Hydromatic measured 13 feet 4 inches across with variable pitch control, sophisticated aerodynamic design paired with hydraulic precision. Japanese engineers grasped propeller theory well enough, but they lacked workshops capable of producing large propellers with the necessary accuracy. Throughout the airframe, the same pattern kept emerging. Landing gear mechanisms were intricate yet flawlessly made. The instrument panel in the cockpit displayed far more gauges and controls than anything found in Japanese fighters. Fuel tanks incorporated self-sealing rubber compounds that swelled upon puncture, stopping fuel loss instantly, technology Japanese aircraft mostly did without. The electrical wiring ran throughout with quality insulation, properly organized to power comprehensive equipment. Most striking of all was the consistent excellence across everything. Major structural components and tiny fasteners alike reflected careful workmanship. Aluminum alloys maintained uniform properties. Steel had been properly heat-treated. Surfaces gleamed with professional finishing. The entire aircraft felt solid and durable, built to endure. This overall quality stood in harsh contrast to what Japanese factories produced by 1945. Wartime material scarcity forced increasing compromises. Aluminum quality had declined. Experienced workers had been drafted into military service. Factories operated under constant bombardment threat from American raiders. Quality control crumbled when production quotas demanded speed over excellence. The captured Corsair examination unfolded as Japan teetered on the edge of collapse. B-29 super fortresses were methodically obliterating Japanese cities. The Navy lay in ruins following recent defeats. American forces had retaken the Philippines, secured Iwo Jima, and were assaulting Okinawa. Against this backdrop, studying an American fighter took on grave meaning. This wasn't intelligence gathering for some future comeback. This was a confrontation with technological truth. Engineers at Yokosuka and Tachikawa prepared detailed technical reports. They recorded measurements, described manufacturing processes, and assessed American capabilities with professional distance that couldn't quite mask deeper implications. In almost every aspect examined, American technology surpassed what Japan could produce. The gap wasn't marginal, it couldn't be bridged quickly. It reflected years of industrial investment, enormous research spending, sophisticated factory networks, and resources Japan's ravaged economy simply didn't possess. By August 1945, when the war ended, Japanese forces had captured at least 2 Corsairs. Evidence indicates technical teams successfully repaired at least one toward operational status, as photographs show captured aircraft with patched wings and fuselages. Whether this aircraft actually flew remains unclear, but repair attempts suggest genuine determination to get one working for testing. When American troops reached the Yokosuka Naval Air Technical Arsenal in September 1945, they encountered extensive proof of Japanese technical investigation. Allied aircraft sat scattered across the grounds. Technical files, technical drawings, and photographs documented Japanese efforts to comprehend American technology. American intelligence personnel seized everything, understanding its importance for learning what Japan had discovered. The Corsair examination represented something beyond mere technical intelligence gathering. It symbolized the immense technological gulf separating the two nations by war's end. When Corsairs first saw combat in early 1943, skilled Japanese Zero pilots could still hold their own through superior tactics and experience. By 1945, even experienced pilots in newer aircraft faced impossible odds against well-trained American Corsair pilots. The aircraft's technical advantages, combined with America's numerical strength and superior pilot instruction, created hopeless situations. The Corsair achieved an impressive 11-to-1 kill ratio against Japanese fighters. American Corsair pilots downed 2,140 Japanese aircraft, while losing just 189 Corsairs to enemy action throughout the entire war. These figures reflected far more than one aircraft's superiority. They demonstrated the totality of American military advantages: better training programs, stronger supply lines, unlimited production capacity. advanced technology across every system. Japanese engineers studying the captured Corsair grasped all these realities. They could measure the performance gap, examine the manufacturing distinctions, and calculate resource differences. Their reports stand as admissions of Japan's inability to match American industrial power. The Corsair itself continued flying long past the war's conclusion. It served through the Korean War from 1950 through 1953, excelling in ground attack and close air support missions as jet fighters assumed air superiority duties. Allied nations, including France, flew Corsairs in colonial conflicts throughout the 1960s. The final combat missions came in July 1969, during a brief conflict between Honduras and El Salvador. On July 17, 1969, Honduran Captain Fernando Soto, piloting an F-4U, shot down 3 Salvadoran aircraft, including 2 FG-1D Corsairs, marking the last combat victories ever achieved by this aircraft type. Ironically, these final victories came against other Corsairs. From its maiden flight in 1940 through combat missions nearly 3 decades later, the Corsair ranked among history's most durable and successful fighter designs. For Japan, the Corsair encounter formed part of a broader reckoning with industrial reality during the American occupation period. Japanese engineers and scientists who had battled material shortages and manufacturing constraints throughout the war now collaborated with American occupation officials rebuilding Japanese industry. Insights gained from analyzing American technology, particularly the Corsair, reshaped post-war Japanese manufacturing approaches. The commitment to precision, quality control, and perpetual improvement that defines contemporary Japanese manufacturing originated partly from these hard lessons learned while examining what American factories could accomplish. The Corsair, recovered in early 1945, symbolized more than a destroyed warbird. It embodied engineering achievement and manufacturing excellence that Japanese aviation had pursued throughout the conflict. The lessons came too late to alter the war's outcome, yet they influenced the reconstruction that followed. Confronting this American fighter, Japanese engineers faced the full scope of what they had opposed. They possessed courage and capability, but those qualities could never overcome the technological and industrial superiority arrayed against them. The story concludes not with victory, but with acceptance. Japanese technical reports on the Corsair, discovered by American occupation personnel and now preserved in archives, serve as quiet testament to a moment when one nation's engineers measured themselves against another's capabilities. The specific Corsair under examination has long vanished, probably scrapped in the confusion of the post-war years. Yet what it taught endures. The lessons revealed what could be achieved when technology received adequate resources, sophisticated manufacturing, and genuine industrial capacity. Japanese aviation would eventually recover, yet never again would Japanese engineers underestimate American technological capabilities when given proper resources and knowledge. The 1945 Japanese technical examination of the F-4U Corsair stands as a turning point. The instant when Japan's aviation community finally comprehended the technical abyss that had widened throughout the war years. It was a lesson inscribed not in reports or strategy discussions, but in aluminum alloys, precisely forged components, and manufacturing tolerances that communicated more forcefully than any words ever could about the reality of American industrial strength.